Have you ever wondered about the mysteries that the cosmos holds, the secrets locked away in the dark recesses of space? The universe is a vast expanse of unexplored territories, and one of its most intriguing enigmas is the black hole. Born from the gravitational collapse of massive stars, black holes stand as some of the most fascinating objects in our cosmos. They are entities of intense gravitational fields, powerful enough to warp the fabric of space-time itself. They have been the subject of scientific scrutiny and public fascination alike, capturing our imagination with their mysterious nature. They are not just celestial curiosities, but essential keys to understanding the universe. They challenge our understanding of physics, test the limits of our theories, and offer a glimpse into the extreme environments of the cosmos. Today, prepare to delve deep into the abyss as we explore the formation and phenomena of black holes. To understand black holes, we must first understand the life cycle of stars and the force that governs them: gravity. Our journey begins in the dense, cold pockets of interstellar gas and dust, where stars are born. These regions, known as molecular clouds, are the cradle of star formation. When a segment of this cloud collapses under its own gravity, a protostar is born, marking the start of a star's life. As the gravitational force pulls the cloud's gas and dust inward, the protostar grows denser and hotter, with its core temperature rising. When it becomes hot enough, nuclear fusion ignites, and the star begins to shine, entering the main sequence stage of its life cycle. This is the longest stage, where a star like our Sun will burn for about 10 billion years, converting hydrogen into helium and radiating energy in the form of light and heat. But what happens when a star exhausts its nuclear fuel? Stars of different masses meet different fates. Smaller stars, like our Sun, swell into red giants before shedding their outer layers and leaving behind a white dwarf. However, stars with masses greater than about 8 times that of our Sun undergo a more dramatic transformation. When these massive stars deplete their nuclear fuel, gravity takes over. With no outward pressure from the fusion to counterbalance it, the star's core collapses under its own gravity, leading to a spectacular explosion known as a supernova. What's left behind is a dense core, which, if massive enough, can collapse further to form a black hole, one of the most mysterious entities in the cosmos. When stars exhaust their nuclear fuel, things take a fascinating turn. Our journey into the enigma of black holes is just beginning. As we delve deeper, we'll explore how these remnants of massive stars warp space-time and why they continue to captivate us. When a star exhausts its nuclear fuel, it collapses under its own gravity. But what happens when the star is massive enough? This is where our cosmic tale takes a fascinating twist. You see, stars live a life of balance. The outward push of energy from nuclear fusion in their cores counters the inward pull of gravity. But when a star burns through its nuclear fuel, that balance topples. There's no more energy to hold gravity at bay, and the star begins to collapse. Now, for stars around the size of our Sun, this collapse is stopped by the repulsive forces between closely packed electrons, resulting in a white dwarf. But when we're dealing with a truly massive star, say about 3 times the mass of our Sun, even this electron repulsion isn't enough. These massive stars undergo a more dramatic fate. As they burn out, their iron core collapses under the immense pull of gravity. In a fraction of a second, the core shrinks from thousands of miles across to a mere few, causing the star to implode. The outer layers of the star are then blasted away in a spectacular supernova explosion. But what's left behind? Well, the core continues to collapse, condensing into a point of infinite density known as a singularity. Around this singularity, a boundary forms where the escape speed equals the speed of light. We call this boundary the event horizon. Anything, matter, light, your lunch if you're unfortunate enough, crossing this boundary is sucked in, never to return. This, my friends, is a black hole, an object so dense with such an intense gravitational pull that not even light can escape its grasp. So, a black hole is born from the remnants of a massive star. But what exactly is a black hole? This is the question we'll be diving into next, as we unravel the enigma that is a black hole. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape it. Now that's a statement that can make anyone's mind whirl. But let's break it down and explore the intriguing anatomy of a black hole. At the very heart of a black hole, we find a singularity. This is a point of infinite density where our understanding of physics, as we know it, simply breaks down. It's like the universe's version of a do not enter sign. The singularity is hidden within a boundary known as the event horizon. This is the point of no return. Once something crosses this threshold, it's forever lost to the black hole's insatiable hunger. Surrounding the event horizon is the accretion disk, a swirling vortex of dust and gas that's been trapped by the black hole's immense gravitational pull. This disk heats up due to intense friction, causing it to glow brightly. It's a bit like a cosmic lighthouse, signaling the presence of a black hole. Interestingly, not all matter in the accretion disk gets swallowed. Some of it is shot back into space in what we call jets. These are powerful streams of particles, propelled at nearly the speed of light, along the black hole's axis of rotation. However, it's not all doom and gloom in the vicinity of a black hole. There's a peculiar phenomenon known as Hawking radiation, named after the brilliant physicist Stephen Hawking. He proposed that pairs of particles and antiparticles spontaneously form near the event horizon. Usually they annihilate each other, but sometimes one particle escapes while the other falls into the black hole. This escaping particle is what we observe as Hawking radiation. Black holes, as we've seen, are fascinating and complex, but how do we even know they exist? Well, stick around and we'll delve into the captivating evidence that proves these cosmic beasts are more than just figments of our scientific imagination. Despite being invisible, black holes can be detected and studied. How so, you might ask? Well, the answer lies in their immense gravitational pull and the effects they exert on their surroundings. Since black holes don't emit light or radiation we can detect directly, we have to be a bit clever. We look for the telltale signs of their presence, the cosmic breadcrumbs they leave in their wake. One of the most common ways we find black holes is by observing their gravitational influence on nearby objects. Imagine a star moving through space. If it passes close to a black hole, the star's trajectory will change, veering towards the black hole due to its intense gravitational pull. By tracking these changes in motion, astronomers can infer the presence of a black hole, even though they can't see it directly. Another indirect method of detection is through the observation of accretion disks. These are swirling rings of matter spiraling into a black hole, superheated by the intense gravitational forces to such high temperatures that they emit X-rays. These X-rays can be detected by telescopes, providing another pointer to the presence of a black hole. And let's not forget about gravitational waves. These ripples in the fabric of space-time were first predicted by Einstein, and their discovery has opened up a whole new way to probe the universe. When two black holes merge, they create a cosmic symphony of gravitational waves that can be picked up by detectors here on Earth. So, while black holes might be elusive, they're far from invisible if you know where to look and what to look for. Each method of detection offers a unique glimpse into these cosmic enigmas, and together they paint a picture of a universe far more fascinating and complex than we ever imagined. Black holes, once just a mathematical curiosity, are now a tangible reality, each discovery peeling back another layer of the cosmic onion. Our journey through the cosmos has brought us face to face with one of the universe's most enigmatic phenomena, black holes. We've delved into the depths of stellar evolution, gravitational collapse, and the extreme physics that give birth to these cosmic entities. We've explored the life cycles of stars, the explosive supernovae that herald the birth of black holes, and the intricate dance of matter and energy around their event horizons. We've marveled at the diversity of black holes, from stellar remnants to the supermassive giants lurking in the hearts of galaxies. And we've grappled with the quantum paradoxes of Hawking radiation, where the laws of physics as we know them are stretched to their limits. The mysteries of black holes continue to captivate us, fueling our curiosity and driving us to explore the uncharted territories of the cosmos. Our journey to understand the universe is far from over.